Good afternoon, everyone. I'm Professor Sever, and today we're going to look at a series of videos that will all ultimately involve the same base special trigonometric limit, namely sine x over x as x goes to 0. So let's take a look. Now we know that this limit is 1, and we're going to use this result to evaluate the following 8 problems. So let's get started. Okay, so for our first problem, as we would with any problem, we want to investigate the form of the limit, the basic form of the limit. And we will see as x goes to 0, the denominator goes to 0, and as x goes to 0, the numerator goes to 0. When we analyze it in this fashion, we get the indeterminate form 0 over 0. This says that we have to do more work. In other words, we cannot tell or determine what the limit is by that low level of analysis. So remember, at each stage, you need to write the limit. You just don't want to do the work without having the limit there. Let's go ahead and factor the denominator. Let's just leave the numerator alone. So it's 2 times sine x. And if we factor the denominator, we will see x times x over 3. And if I were to highlight these terms, you see right here, in this portion of the problem, we see our sine x over x. In fact, I went ahead and recopied our original result here so we could use it. I'm calling it this knowledge base. So that's the knowledge that we're going to use in this problem, along with some other basic knowledge of limits, some technical knowledge of limits. But let's see what we've got here. So this says we can separate the limit into the following 2 pieces. Limit of one of the terms times the limit. So you see here I have the original quotient separated into 2 pieces, and now we can do this separation. In other words, we can separate thusly if the limit of both of these pieces. Well, this one does, as we'll see, through direct evaluation. And of course, this is our first favorite trigonometric limit we have here. So on the next step, okay, so for the limit in purple, so for that rational function, we evaluate the limit in purple by direct evaluation. That will be 2 over 0 minus 3. And of course, the second factor is the entire point of this video. That is the value of 1. There's no limits on this stage, because I evaluated the 2 limits. Now, what is this equal to? This is negative 2/3. Okay, once again, I always encourage you to pause the video so that you can see what was done. Hopefully you follow that step. Okay, let's look at our second problem. And again, what we're going to do is separate this. So you see, first off, what's sine squared? Well, that's sine times itself twice. So that's sine times sine. And again, now you're probably anticipating what I'm going to do. See, here's your sine x over x, which is the limit that we want to attack in this problem, so to speak. We're trying to do some algebraic or trigonometric moves so that we can flesh out this piece. So again, I'll separate this now. The limit of the product of the limits, provided the limit of both of those. This piece, and again, both of these pieces. This is 0. And this is our favorite limit. 1, and again, I didn't mention it here, and this is the first thing that you always look at. I did it kind of mentally and moved on. Let me analyze the basic form as I did in the previous problem, and you'll do this in every problem. The bottom goes to 0. Of course, the top goes to 0. So again, you have this indeterminate form of 0, 0, which says you need to do more work. Okay, and then continuing, done. So what is this limit? All right, so for the limit there in purple, the answer is just 0. The product I wrote there is just that product. And now again, what's this limit in red? That's just the number 1. And 0 times 1 is 0. So in this new problem, I've added to our knowledge base. And let's see what we've got. So let me explain what this new fact is, or theorem. So if you're working on a limit problem of a fraction, and if the top doesn't go to 0, say it goes to a number like 5 or 1, other than 0, and the bottom goes to 0, then we know that this limit doesn't exist. And that's what we're working on here. We should remark that at this time, this limit is geared only to determine whether the limit exists or not. Later, when we know a little more and discuss infinite limits and one-sided limits, you'll have to do a little greater level of analysis to determine whether the limit is infinity or perhaps minus infinity. But at this time, this theorem only goes as far as to say that the limit does not exist. Later, we will have to do more work, as you'll see in my subsequent videos. Okay, so let's work this problem and see if this fact comes into play. Well, again, the first thing you want to do is look at the form. You have the bottom goes to 0, certainly. The top, again, is going to 0. We have our 0 over 0 form. That's indeterminate, which means you can't tell just by looking at it. And therefore, we need to do some work. We need to do some analysis on it. Okay. So let's see. Let's come back and review. In the first problem, our indeterminate form, the original problem had the indeterminate form 0 over 0, and the answer was -2. In the second problem, we had our indeterminate forms 0 over 0, and we'll see what happens in this third form. I guess we're foreshadowing it. Let's rewrite the function this way. Sine x over x all over x. All right, so what's happening here? Well, the bottom certainly goes to 0. That's what's happening here. See, g of x is on the bottom. Now, what about the top? Well, where does the limit of sine x over x as x goes to 0 go? So this goes to 1. So this goes to 1, which is non-zero. The bottom is going to 0. So this limit doesn't exist. In fact, that's all we really need. All right, then the limit, that's equal to 1. And the key is it's the fact that 1 is not 0. And limit of the denominator is 0. As this gives us a non-zero number, 0 form, and of course that tells us the original limit doesn't exist. And let's look at our fourth problem. And this is a classic, and this is technically what we call change of variables. So here, first thing we want to do, let's move the 5 outside, which is on the in the denominator, 1/5. Remember, constants can come outside the limit. Let t equal 3x. Okay, so now we have to compute the limit. As x goes to 0, our original variable, where does t go? 3 times 0 is 0. Let's look at our original problem. So 3x started the whole process. That's going to be t. Well, but what's x equal to? So here we need to do a little solving. So if t is equal to 3x, then divide both sides by 3, or so 1/3 t. So now write the original problem rather in terms of t. Numerator will be sine in place of x. What's x equal to? Well, that's 1/3. And that's what I'll do and now 1/5 is still outside. As our new variable, t, not x, goes to, now we got to be careful, it's this 0. Not this one, this 0, keeping with the colors. All right, and it's sine of t over what? Well, t over 3. So this is, now the fraction over a fraction, that will flip, take the reciprocal, so that, and you can pause and make sure you do the math here. The 3 will come outside. So 3/5. All right. And now here is our favored limit again, the one we said we were going to work on. What is the limit? This is a classical problem that's done in every single calculus book. And again, I didn't say it. Did it mentally again. We have 0 over 0 form. That's why it's indeterminate. You can't tell just by looking. Okay, our next problem. Now this is different. This is a variation of the last one, but notice 2 problems ago rather. So notice 2 problems ago the squared was in the denominator. And in the second problem, the sign was being squared. So here the squared is taking place inside the argument of the sign. So here's what we want to do. All right. And now we're going to multiply by the number 1. Of course, all this is inside the limit, but we're gonna choose x for x. All right, let's see what we've got. Let's combine. I don't want to separate yet. All right, so now I've got x times sine of x squared over x squared. And here's the part that matters. Now notice the key is whatever the argument is here, that's the same what we have in the denominator. So we're going to separate it as we did before. Limit. Okay, so now I'm going to separate it into two limits. You can't just look at this piece and stop and say, and this is really probably a good point, but look, you can't just stop here and say, okay, look, what is this piece? Well, this piece is going to 0. What's 0 times anything? Well, anything that exists. 0 times a number is 0. So if this limit exists, then certainly this answer would be 0. And by the way, if either of the two, by the way, this one or this one did not exist, then that separation would not have been justified. And if you were wondering where that times was, there. That product, that one. So technically, we still have to evaluate both pieces. So this piece we know, that's simple. That is 0, but we have to wait to finish to get the second piece. Now here, I'm going to let t equal x squared. We have to compute our new limit. So as x goes to 0, t goes to 0. But really, and if you wrote that, that would be kind of okay, and it depends on where you are in your course. When you get to the point of studying the one-sided limits, you really need to put 0 from the right. And technically it's 0 from above here. And if you left it off, it would be, but it wouldn't be demonstrating your full knowledge of the limit. You didn't do that. All right, so now what's our new variable, t? Where's t going? T's going to 0, right? And then this is sine t over t again. And what is this limit? This limit's 1, so it exists, and therefore this limit is 0. So we get 0, 1, and that's the final answer. So let's take a moment and look at this right. So if we were to graph it, and this is kind of not a digression, it's explanation what's happening here. Okay, so if we were to graph it, to graph the change of variables, let me do it in blue. Now, so this is the t-axis. This would be the x-axis. And we would have our t equal x squared as a parabola. Kind of sloppy, but anyway, that's the parabola that I was quickly drawing. Now notice as x goes to 0, the t values, which are the y values in a classical xy coordinate system, the t values are going to 0, but above the x-axis. They're all going to 0 from the positive side. And as x went to 0 from the left, the t values are going to 0. Again, all above the x-axis. A little more technically correct to put it. Well, this is our next problem. Well, we really just did it. This is the exact same problem that we did right here. Okay, on this problem, once again, this is again 0 over 0. As you know, which is an indeterminate form. All that says is that we're going to start to do something else in terms of the limit process. So here we have x is going to 0. And here I'm going to multiply again by the number 1, special version of it, which will be helpful in this problem, by 1 again. But for this time, I'm going to choose the following version of the number 1 over x, anything over itself, right? 1 over x over itself. All right, so this is the limit as x goes to 0, 7x over x. And now we obtain the following. Continue the problem down here. Now, unlike last time, watch what I'm going to do. I'm going to multiply again rather than doing this all. I have to do change of variables twice. We need the argument of the sign to match the denominator, but we have that twice. So watch, I have 2 different numerators, 2 different denominators. So in the top, I'll do it in blue. I'll multiply again by the number 1. 7 over 7, and in the denominator 2 over 2. I'm going to multiply these two together. That'll be 2x on the next step. So it'll match this. I'll do the same thing here. And then this 7 will come outside, and this 7 will come outside in the numerator, the denominator, namely. Again, I always encourage you to work this out if you're watching. Sometimes it's nice to watch and not do the work, but all right, so this is sine 7x over what? Sine of 2x. And you should see now this argument matches the denominator here, this argument of 2x there. So again, we're going to split the limit of the numerator, limit of the denominator, and do two change of variable techniques separately. I didn't actually write out. So see here we have the product and this product. So I wrote it out as two separate limits. So I'm going to do it as the quotient here. So now, let me colorize it. Big fraction bar. So now, and let's not forget 7/2 still out front. All right, so now in the numerator, you're going to have a limit. In the denominator, you're going to have a limit. In the numerator, the limit's going to 0, same as the denominator. Now this is sine 7x over 7x. So really what we need is, now colorize them. All right, so for the yellow one, and hope the green, I'll work out two different change of variable. Because why? We have two different matching arguments that we have in terms of the composite function. All right, so for the top, the yellow one, I'll do it in red, let's say. Here, I'm going to let t equal 7x as x goes to 0. T goes to 0. Okay, now we have a separate substitution. Do it in green. And you can use t, but I think it's better form to use a different variable. Technically, these are separate limits, and we shouldn't get confused, although with the t being in both places, but let's just avoid that. Let u equal 2x. As x goes to 0, u goes. Okay, so let's rewrite now. Limits. Okay, so now we have the limit. Don't forget our constant out front, 7/2. Easy to do, but it's sitting right here. All right, times. All right, times the following quotient. The limit as t goes to 0 of sine t over t. This is the limit as u, different variable, sine u over u. And to match it, this was the highlighted yellow one from the previous step. Now both of these exist, and neither is 0. This goes to 1, this goes to 1. So the answer should just be 7/2 times 1 over 1. And that's it. That's our answer. 7/2. And that's a lot, and it's easy to skip those steps or not understand the importance of doing those steps. Let's just take a moment. But technically, it's double substitution, and we added this in to make it work. We don't want to just go, look, some people would say, look, see the 7/2 here, you can pull them outside, and the answer is 7/2. That just doesn't work. It doesn't work that way. It's somewhat coincidental that you do get that number, but that's certainly not how the work would look. Okay, and for our last problem, or our 8th problem, again, now this one's interesting. It's not 0 over 0 form. Cotangent is cosine over sine, cosecant's 1 over sine, so both of those are undefined at 0. So it's undefined over undefined when you analyze that. And of course, that's not a determinate form either, which again, all it says is looking at them separately, individually, as x is going to 0, and then saying, can I form the ratio of the results? It doesn't work because none of them is defined. What we want to do is fall back to our basic knowledge of trig. And let's actually pause here. What would my knowledge base be? So our knowledge base would be that. Of course, we're going to use that at the end. We would also have that cotangent of x is equal to what? Cosine of x over sine of x. Need that. And number 3 would be that cosecant of x is 1 over the sine of x. So that's our plan, to write each of these two functions in terms of sine and cosine separately. And again, we're going to have a complex fraction. So what's the numerator? Well, it's cosine of 3x over sine denominator is 1 over the sine of 4x. Again, certainly being a little bit more correct, putting in our parentheses. All right, now let's simplify this algebraically. Cosine 3x times. So in this case, we're dividing two complex fractions. So the old keep, change, flip motif comes in. You take the reciprocal of the denominator and multiply. That problem before, this is virtually identical to this. You see you have two signs over each other with two different arguments or angles. That's what we have here. So we're going to parallel the two substitutions that we did before. And cosine I can just separate out as a product. So let's do that. And again, I'm putting in all the steps. You could, once you become a little more adept, you can write it out a little more fluently, but here's how it's going to go. And again, just to give it away, let's multiply 1 over x over 1 over x. Remember, that'll be the number 1. And sine of 4x over x in the numerator. Sine of 3x over x in the denominator. Let's go ahead and prep as we did. 4 over 4, that's 1. 3 over 3, again, what am I shooting for? These be the same. So the 4/3 will come out, and I'll go ahead and write it all the way out front of everything. And again, this is just 1. You don't want to do that now because, you could, but you shouldn't. That's a matter of style. I shouldn't say you shouldn't say that. It's best to wait because, again, you don't really know that this is justified, this separation, until you get the limit. Both of these limits exist. It's the way we write it. And it's just a legacy way we write it. So we're assuming everything's going to work out, and it will. So this is 4/3 limit. X goes to 0. Cosine times. Okay, well now we're going to do it as we did on the last problem. The limit of the quotient is the quotient of the limits. So we're going to separate this into the limit of the numerator and denominator. So in the numerator, we obtain the limit as x goes to 0 of sine of 4x over 4x. And in the denominator, we obtain the limit as x goes to 0 of the sine of 3x over 3x. You may want to pause the video here, see if for the numerator, t is going to be 4x. For the denominator, u 3x as x goes to 0. T goes to 0. For the denominator, where does u go? 0. So this next step here, this will be final moment where I'll evaluate all the limits. Okay, so here I have the limit as t goes to 0. Sine t. In the denominator, the limit as u goes to 0 of sine of u over u. As we have seen repeatedly throughout this video, each of those limits separately in the numerator and denominator go to 1. So now that everything's ready, let's evaluate each limit. 4/3 is constant. Nothing's happening there, so copy that down. All right, now this one, as x goes to 0, what is this limit? Well, that's just cosine of 0, 1. And now this limit is our first favorite trigonometric limit being applied twice. So it's 1 over 1. And now what is this equal? Remember, the cosine of 0 is 1. And that was our last of our 8 problems, all showing different ways our favored limit, sine x over x, can appear. And I hope you found this video instrumental or enjoyable about this problem. Hopefully you'll feel a little bit better about using this technique. I'm Professor Sever. We'll see you next time.